Assalamualaikum warahmatullahi wabarakatuh, and good day. Thank you for watching this video, and also thanks for those who already watched my previous video under the subject of instrumentation and control system. This video, for this session, I hope that you already watched the previous one, because otherwise you will have difficulties on understanding a few terms that I will use in this video. So the topic for this video, or for this lecture, is the introduction to data acquisition system with the help of virtual instrumentation software, the Z-Lab. I will move side by side. I will explain the theory, and I will use the software to make sure that we have a good understanding on the theory that I introduced. Okay, so this presentation, this lecture, I will divide into two parts. The first is about the transforming the signal, the physical signal or engineering quantities into electrical signal. This is all about the signal conditioning elements, if you still remember. And then the second part of this lecture is about the signal processing, basically about the digital signal processing in time domain and frequency domain. Before we go further to the data acquisition system, or DAQ, I would like to ask you to recall a little bit on the sensors that we already learned, we already discussed in the previous lecture. For example, in the previous lecture, we introduced about the accelerometer that convert the acceleration into the electrical signal, is the dynamic signal as the output. And then we also have thermocouple that give us temperature. For this case, the transducer, the sensor, convert the temperature into electrical signal. Basically, all of these sensors, they convert the physical signal or physical quantities, like I said, acceleration, temperature, displacement, strain, dynamic force, sound pressure, sound intensity, rotational speed, pressure. All this physical quantity is being converted into electrical signal, because in the scope of our study for developing the instrument, we need electrical signal, because it will easily processed further if you transfer the signal into computer or into microcontrollers. Alright, so like I said, all the physical quantities converted into electrical signal, but the relation between these two things, the electrical signal and the physical quantity, they have a proportional relation. We call it as sensitivity. All right. For example, the units usually we use volt per engineering units. Any engineering units, if accelerometer is acceleration, or G for the temperature. For the thermocouple, we have temperature units, for example, Kelvin, degree C, and any that relate to the temperature. And the same goes to other engineering quantities, or same goes to the other sensor that give us information about the engineering or the physical quantity. Let's say we have example of accelerometer that have sensitivity of 100 millivolt per G. The G here is refers to the meter per second square, the acceleration itself. So with the 1 G, it will give 100 millivolt of electrical signal. Okay, so let's say if we see the instrument that measure the acceleration, we see the value of 1 volt. For this sensitivity, it means that it gives us 10 G value. Okay, so this is what the sensitivity looks like. It's actually a relation between the electrical signal and the engineering units, engineering quantity. So basically it's in linear, so it's easy for us to predict, it's easy for us to relate between the quantities and the signal. But however, the linearity it's affected by a few parameters. For example, we have frequency also can affect the linearity of the sensitivity. Temperature, maybe it also affect the sensitivity. Distance, pressure sometimes. So we have to make sure that our linearity, the effect of other parameters to the linearity is minimum. Otherwise, it will affect the measurement. It will increase the uncertainty to the measurement. So now we go in detail about the data acquisition. It is an hardware. Basically, it's hardware. It involves a few components. I will go explain a little bit detail after this. But first, I want you to recall our basic understanding on the fundamental of elements that need to have in a complete instrumentation, which is we need to have a sensing element, signal conditioning elements, signal processing elements, and display element. So as I mentioned earlier, this is the first part where I will introduce about the how to convert the electrical signal, physical quantity into electrical signal, which is about the signal conditioning elements. So for these signal conditioning elements, we have 4 components, 4 parts, which is signal conditioner and amplifier, and the second one is anti-aliasing filter, and the third one is sample and hold function, and then last one is of course the analog to digital. At the end, the electrical signal will be converted into a digital signal. So for this signal conditioner and amplifier, what it do is first it provide the power to the sensor. Some sensor need to have powers to operate. So because of this is the first part, the first component that connect to the sensor, so it give a power to the sensor. And the second one, the most important, is this component here. It will condition the signal to give the signal that the best signal or the appropriate signal that can be used for further processing. For example, if the signal is low in amplitude, it will amplify it using amplifier. And if the signal is embedded in the noise, also the noise floor is quite high, or there is a lot of unwanted signal that involved in the signal that we measure, so we must filter it. So 2 things: we amplify the signal and we filter the noise. Okay, and then after we condition the signal, and it is good to be used for further process, we will introduce the anti-aliasing filter. But before we go to the anti-aliasing, we need to understand the aliasing phenomena. But before aliasing phenomena, I need to introduce a few things. I have to introduce about the sampling process. But first, we have to answer the question, why sampling need to be done? Because we know we want to convert the analog signal, and analog signal cannot be understood by computer or any other microcontrollers. They only understand digits, digital number. So we have to convert into digital signal. So with that, to achieve that information and to achieve that function, so we have to do sampling. So in the signal conditioning elements, which is a hardware. It have a circuit, is electronic circuit that can sample the signal, and at the end it will give us the digital signal. We need to understand a few things about the sampling process. First, we need to understand the term for the sampling, which is the sampling frequency. What is actually sampling frequency? It's actually we give if we have analog signal, we convert it into a sample. But first, we have to understand what is sampling or sampling frequency. So we know that we want to convert analog signal into digital signal. Analog signal is continuous. The digital signal is a discrete signal. So discrete signal require us to sample the analog signal. So the sampling process is defined by for the sampling process, we need to know two things. First, the sampling frequency, and the second one is the sampling period. So the sampling frequency is the relation between the sampling frequency and the sampling period is inverse with each others. So sampling frequency is Fs equal to inverse of sampling period. Sampling period is the distance between two sample that can represent a analog signal. Okay, so this is example of an analog signal being sampled. Let's say we have a signal with 1 cycle per 10 second. Let me write it down here. F equal to 1 cycle over 10 second. So we have 0.1 Hertz signal, and then it being sampled with 10 sample per 10 second. So we have Fs, sorry I write it up here, 10 sample over 10 second. So it means that the sampling rate is 1 Hertz. 1 Hertz. So easily with the sampling 1 Hertz, so if you want to find the sampling period, just inverse the value. So 1 over 1 is 1, of course. So the sampling period Ts is equal to 1 second. You also can see this in the figure. So we see here is actually 1 second. So 1 second. Okay. So this is example of a random signal. The red dot here is the sample. The number of sample, we call it block size. For example, for this case, for one block, the duration for one block is t second. The distance between two dots is sampling period, as I mentioned earlier, and the sampling rate again just inverse of the sampling period. So the relation between sampling period, sampling frequency, time for one block, and the block size is given here. So let me make it clear. So we have Ts equal to T, the time for one block, divided by number of samples in the block, or we can say the Fs equal to N over T. It just inverse between with the Ts. So let's say we want to find how long the block, the duration of the block. So we can set the sampling rates. Let's say we have 1,000 sample per second, and we also can set the number of sample that we want. Let's say we set about 2,000 sample. So by using this equation, we can calculate the duration of the one block. So let's say we have here, so from the equation we can find the n over fs, so we can find the value for t, the time. So for this case, this example, so 2000 over 1000, so it gives us 2 seconds, the duration for the measurement or for the signal. Alright, now we come to the problem that I mentioned earlier, the aliasing. So if we're not giving appropriate sampling to the signal, it will give this problem. So what is aliasing? Aliasing actually is the phenomena where the higher frequency signal comes into the our DAQ, but the DAQ have limitation in sampling frequency. So we set it lower, far lower than the frequency that comes in, the signal that comes into the DAQ. So with not enough sampling, it will give the output signal which is lower frequency than the first signal that comes in. So it will give a false representation to the signal, to the original signal that we measure. So we need to avoid this. So how can we avoid this? So first we need to see the phenomena first. If you see to the figure, let's say we have the top figure, this one. If we sample it right, we can represent the signal correctly. But let's say let's say the red dot is the sample. So for the same sample, if we give the just a low sampling frequency, now if we plot it again, it will give a lower frequency compared to the original frequency. So this is a false representation of the frequency. So we need to avoid this. So how to find the best sampling that can sample the input frequency? So we go case by case, one by one. Let's say we have maximum frequency. The frequency of the signal is 2 Hz, which is 2 cycle per second. Okay. Then let's say we give slightly above sampling frequency slightly above than the 2 Hz, which is 2 times 2/3 Hz. But if you give that sample, still if you plot it again, it will not give the correct shape of the original sample. Let's say we increase further, let's say 3 Hz the sampling frequency, and we plot it again, still it approaching the same shape of the original frequency, but still it cannot show the original frequency. Then we increase to double. We increase double sampling frequency compared to original signal, but it worse. It getting worse. It not even giving us straight signal at all. It will give us just a straight line. So we need to avoid giving the sampling frequency exactly double to the maximum frequency. But if we increase a little bit, maybe 0.5 or 0.1 compared to the maximum frequency, let's say we give 6 Hz sampling frequency, now then we can represent or create the same signal that looks like the original signal. But of course, this one, if you see in the display, it not looks like this. Does not look like smooth like this. It may look like, sorry, actually it should like this, just a straight line, very sharp like this. So this is what you look like in the software or the display after the digital signal. But the thing is, we can conclude that the sampling frequency must be slightly above than double of the frequency that we measure. For the case of we have a lot of frequency, of course the random signal, we have a combination of a lot of frequency, so we need to identify the maximum frequency that we want to measure. So make sure that the sampling frequency is slightly double than the maximum frequency that we measure. So we call it Nyquist sampling theorem. Nyquist sampling theorem. We can say that the sampling frequency must be above than 2 times f maximum in that we measure. Okay, so now we know that the phenomena of aliasing. To minimize the effect of aliasing, we must introduce the anti-aliasing filter. So what is anti-aliasing filter? It is actually a low pass filter that can filter the frequency that above than the cutoff frequency. It allow only the frequency lower than the cutoff frequency. So for the case of anti-aliasing filter, we know that the rule for aliasing, to avoid the aliasing, is we must make sure that the sampling above than double of the maximum frequency. So we need to make sure that the frequency that comes in must be the maximum frequency. It must be lower than half of the maximum frequency. So if we have the sampling frequency of 1000 Hz, okay, 1000 Hz, so we need to cut the frequency so that the frequency it is 500 and less. Okay, so it is important to cut this frequency before we allow the analog to digital converter to function. Okay, this is the representation of the anti-aliasing low pass filter. Say we have a sampling frequency here, so we must make sure that the signal must be half than the sampling frequency. Above that we need to filter. But for the case of low pass filter, it have limitation. So low pass filter, if we introduce it still have leakage of signal. It is actually a limitation of the electronics device. It will still have leakage. Let's say we want to works with 400 Hz signal, so we know that there is a little bit leakage of the low pass filter. So we need to filter the signal around 500 Hz. In other words, if you want to if you set the anti-aliasing filter 500 Hz, you actually can work in about 400 Hz only. Okay. Okay, now we move to the important parts in the signal conditioning element, or the final part of it, which is the analog to the digital converter. Before that, we need to see the amplitude resolution. I need to introduce about bits, because the resolution, we know that the resolution is actually the smallest scale that can be divide, or can be grid for the any range. So the smallest scale is resolution. Say for the amplitude, which is the y-axis, amplitude always give to y-axis. the resolution of the amplitude can be given by d to power of m. So m is a bit. Let's say we have 1 bit, so the resolution is equal to 2 power of m. So for 1 bit the resolution is 2. So the smallest, so if we have x value of amplitude, the maximum range of amplitude, so for the resolution of 2, we just only divide into 2. This is actually the representation of what I said just now. For resolution of 2, it only have 2 stages. So the signal cannot be represented in a good shape. Although we have quite good sampling. See the TS there, over there. The TS is quite small. But if the amplitude resolution is big, I mean it's rough, only 2, so that it cannot give a smooth representation of the signal. Let's say we increase into 2 bits, so 2 power of 2 is 4, so we have 4 stages or 4 grid of the signal. Let's say we increase into 3 bits, 2 power of 3 is 8, the signal become smoother. Some of the digital signal up to this level, it should be okay, but some of the user, it needs better than this. So let's say we increase into 4 bits. See, we have a 16 grid, and then it looks better, a lot better than before. Can you imagine if we have say 16 bits of resolution, so it will give a finest grid, which is about 65,536 grid. So it's very fine, and the signal become very smooth. So the dynamic range of the DAQ is given by the largest signal and the smaller signal. Can we get the largest? The largest mean it can be anything, can be the amplitude or can be the frequency. But for this dynamic, for the case of dynamic range, it's about the frequency. So for one measurement, if we can get a ratio of the high frequency and the low frequency is high, so that means the dynamic range is also high. So of course we want to we want to have a very large dynamic range so that we can measure a lot of frequency. But it is actually affected by a few things, which is first is the analog to digital resolution, the linearity, the bits that I've been talking about just now, the amplifier, so either we can suppress the noise or we can increase the SNR, the signal to noise ratio, and also the performance of anti-aliasing, how we choose the low pass filter for the anti-aliasing, and then also the digital signal processing performance. All these things will affect the how much the dynamic range of our data acquisition. So these 4 things here that can can affect the performance of the DAQ, which is the dynamic range. So if we can make sure that these 4 things is set up properly, we can get quite good dynamic range for the DAQ. I just want to show you how, as a conclusion, I want to show you how the analog to digital performance. See, we have the top one is the analog signal, and the bottom one is the digital signal when it passed through the analog to digital converter. See, although generally it can get the signal in general, but if you can see the peak over here, the digital signal will miss it, right? See, it will miss the peak. Okay, so how to avoid these things? Easy. You just make sure that we have enough sample. If we give the finer sampling frequency to this case, I'm sure that we can get the input, the peak. This is the problem here, because in the original signal, in the analog, in the original signal that we want to measure, we don't know if there is a sharp peak of the signal. Okay, we cannot predict that one. That's why we must make sure that we have enough sample. But the problem, if we have too much sample, it will give us problem in terms of storage, because one sample, one bit. Okay, so if we get, let's say, million sample only to measure a short period of signal, so if maybe we have problem in terms of our storage, right? But if we didn't store the signal, then it should be okay, because there is a application where we only view the signal. We will save the signal after we do processing. That also the same one of things that we can do for our measurement, we want to do for instrumentation. That comes to the software, the virtual instrumentation software, whereby we can set only view a very fast signal, we set high sampling, but for the storage we only can store a relevant information only. Okay, so now we will go further detail on the analog to digital converter. It's actually a hardware that converts analog voltage into a binary number, that we call it a quantization. We quantize the signal from analog signal. Like I said, the analog signal can be random, can be sharp peak, can be very low frequency, can be many things. But if we set a proper quantization, a proper value to quantization, and then we can get correct representation in terms of digital signal. The conversion is discrete, time based, so we must make sure that we have a correct representation of the signal. The A to D converter, you have two parts. First we have the analog side, and then the other one is we have a digital side. So for the analog side, it will be represented by the voltage, the volt. For this case, we say is EFSR. E, the normal usual unit term that we use for voltage. FSR is the full scale range. So this is the maximum range that DAQ, A to D of the DAQ can work, which is let's say, for example, we have 10 volt, so only the range is 0 to 10. That one is in terms of unipolar, but some DAQ or some A to D, some DAQ data acquisition have the A to D that works in bipolar, which is plus minus, let's say, 5 volt. It still give the 10 volts range, but in terms of bipolar, it plus minus 5 volt. So that is the EFSR. So for the digital side, it will be represented by M bit, which is 2 power of m different binary numbers. For example, if we have 8-bit AD converter with the EFSR 10 volt, so it would be able to represent the bit side, the digital side will represent the analog signal with 256 different binary values. Okay, imagine that if we can use higher bits of the converter, say for example just now I choose the example 16-bit, so 2 power of 16 give us 65,536 binary values. So the signal will be very, very fine, so it's smooth, so it's very good for our measurement. We have to make sure that the conversion process, we must consider the error, the quantization error. So what is quantization error? It's actually a ratio between the analog side and the digital side. So for the case of 10 volt of EFSR, and the bit is 256. Okay, so the value for the error is about 0.0339. But usually if we represent the error, we must represent in terms of relative value. So it will use the E input as the relative comparison. So the E is actually the input signal, from the transducer. So the error of the from the A to D converter not only comes from the quantization error, it also comes from the saturation error and also from the conversion error. For the saturation error, let's say we have the signal, the input signal EI, a lot higher than the FSR. So what will happen is the signal will above than this limit. For example, we have 4 volt 2-bit AD converter here. So we have 2-bit or 4 the grid 1 2 3 4 for 2 power of m. So the resolution is equal to 4. So for this case, the maximum is 4 volt. So for the E inputs larger than EFSR, so the signal will give the same value here, and will give the same value for the binary output, although the signal is higher and higher and higher. So it will give a false representation to the signal, and this is actually the saturated error. So we must make sure that we give the input of the transducer, the signal is actually in the range of EFSR. Otherwise, it will give us error. Let's say we have a strain gauge balance recorder scale. We have the range of the balance scale is about 0.5 kilogram, and the output is about 0 to 3.5 millivolt. I can remark here, this is actually the FSI, and this one is FSO. And then of course these two value is proportional with each others, which is in linear. And then the signal is recorded using 12 bits A to D converter with 5 volt range. So we mark here, it have 2 power of n, the m is equal to 12 bit, and then E FSR is 10 volt. So we straight away can calculate the Q. 10 divided by 2 power of 12 is equal to 2.44 millivolt. So for this case, the Q, the smallest quantized value is about 2.44 millivolt. Okay, the smallest resolution of the scale is 2.44 millivolt. Let us see the problem here. So from the question itself, I can see if I can analyze this one, if I can analyze this input and calculating the static sensitivity. So FSI divided by FSO is equal to 0.7 millivolt over kilogram. So for every 1 kilogram, it will move about 0.7 millivolt to increase for 1 kilogram. The problem that we have is the quantization. Each move if a scale is actually 2.44 millivolt. By looking at this information here, it is difficult for us to measure 1 kilogram, 2 kilogram, 3 kilogram. Okay. So what happened is, I think for this case, 3 kilogram is the minimum that we can measure, because for 3 kilogram it will give 2.1 millivolt. So for 3 kilogram, then we can use, then it can compare, it can be measured by the system. So in order for us to measure 3 kilogram and below, we must include the gain, the amplification. So let's say we reduce this one. So we reduce to 1% of the FSO. So 1% of the FSO is equal to 1% FSO is equal to this one. So that is 1% of FSO. Okay, so Q, so now we need to make sure that our Q is 35 microvolt. So we know the original Q is 2.44 millivolt. So we must make sure that we reduce the Q up to 35 microvolt. So what we do is we divide this one. So we know that we can get G is 70. So we introduce the gain about 70 times, then we can measure the value of our weight for 3 kilogram and below. Okay, I hope that you understand this example. Make sure you understand. Okay. So if you see this this equipment here, so all this information here is already inside this DAQ. So this is an example of DAQ. If I can zoom in here, if you can see this part here, it will show us the EFSR about 10 volt plus minus 5 volt, and then the M is equal to 24. Okay, so that's it, our the introduction to the DAQ. So we end up the first part of our lecture. So we will continue with the second part after this. Thank you very much. Assalamualaikum.